I am Arundhati and my friend Samuel, and we are on behalf of Nakshatra, the Space and Astronomy Club of NIT Trichy. It is our absolute pleasure to welcome you all to this special guest lecture.
Today, we are honored to have with us Dr. Biman Nath, a distinguished astrophysicist, cosmologist, educator, and author. Dr. Biman is a professor of astronomy and astrophysics at the Raman Research Institute, Bangalore. His research spans a vast topic of topics in astrophysics, and he has contributed immensely to our understanding of cosmic phenomena. With over 120 research papers to his name, he has been an active contributor to the field of space sciences. His achievements include the Vikram Sarabhai Research Award for Space Science 2005, and he is a recognized member of the International Astronomical Union.
And yeah, apart from being a prolific researcher, he is also an accomplished bilingual author, writing both fiction and non-fiction in English and Bengali. His recent book, Homije Baba, explored the scientific legacy and vision of one of the India's greatest scientific pioneers. His columns in national newspapers like the Indian Express and the Hindu have further popularized astronomy and astrophysics among the public.
Today, he will be delivering a talk on the multicolored universe, where he will take us beyond what human eyes can see and into the full spectrum of electromagnetic waves emitted by astronomical objects big and small, from radio waves to X rays and gamma rays, and many, many more. Modern astronomy has unlocked hidden aspects of the cosmos, helping us build a more complete picture of the universe.
On behalf of Nakshatra, I would like to express our heartfelt gratitude to Dr. Nath for taking the time to share his insights with us today. So, we are truly excited to hear from you.
Yeah, thank you so much. Thank you so much for inviting to your me to your Stardust program, and I'm happy to talk about uh, a new phase in astronomy, which you all may have heard about. That astronomers these days talk about multi-wavelength astronomy a lot, and I have given it sort of colorful title saying that multicolored universe. What I mean is that it's not that universe is actually black and white or not multicolored. It is multicolored. It has different views, hues, and shades, and different colors. It's that some of the colors have been sort of inaccessible to us for a long time, and some of the colors have become accessible, and these that has basically helped us to advance our knowledge of the physical processes that are going on in space and some of the events and objects. And by colors, I meant colors in a very general sense. I meant different frequencies, as one of the organizers have, I think Samuel, right, your name, mentioned that. What I mean is the different frequencies. Now, we all know that light is an electromagnetic wave, and wave has different frequencies, right? And astronomers mainly depend on electromagnetic waves, light, radiation, for the information from celestial objects. Although that's not strictly true, this is not the only possibilities. There are sometimes particles that astronomers detect coming from celestial objects, which are cosmic ray particles, are very highly energetic particles. And these days, astronomers are also detecting gravitational waves, which are not radiation, and also, for example, neutrinos, right? So these are also sources of our information, but for most of the time, astronomers do depend on electromagnetic waves. So, and that is what I want to talk about. How certain frequency ranges, which were difficult even century or even 50 years ago, now have become accessible to us, and how it has helped us advance our knowledge. So, do you see my slides, or do I have to? Do you see my slides?
Not yet, sir.
Oh, okay. So I have to share it, right? Right. Sorry about that. Right, right. So can you do that? Can you
Yeah,
see
we
that
can
now?
see it now.
Okay, fine. So I will make it uh, full. So that's like full screen. Is it full screen?
Yes,
Can
sir,
you hear
yes.
me? Yeah. Okay, fine. Okay, so as I mentioned, as I said, just said, electromagnetic waves. This is what light is, and it has got many frequencies. Waves can come in different frequencies, and the different frequencies have got different names. For example, in the visible range, the range of electromagnetic waves that our eyes can detect has a range of wavelength starting from say about few hundred, say 400 nanometers to about 700 nanometers. And so the shorter wavelength, on the shorter wavelength side we have violet, blue side, and then as the wavelengths increase, we perceive a different color. Right? It's a green, yellow, orange, and then red. And then if you increase the wavelength further, our eyes are unable to detect them. That is the infrared range. And beyond the short wavelength, if you make the wavelength shorter than that of violet, say about 300 or 200 nanometers, our eyes again will not be able to detect. That's like ultraviolet. And if you decrease the wavelength even further, so this is the total range of, I mean, what I mean by total range, it actually goes formally from 0 to infinity, right? So, so this is the very short wavelength. Can you see my cursor by any chance?
Yes, sir, we can.
Oh, you can say, oh, fine, good, very nice. So on the right hand side is the short wavelength side, and on the left hand side is the long wavelength, right? And in between, in the middle, there is a range which the light that we can see, and that's the visible range. And on the at the bottom, there are some objects which are being compared to the whose sizes are comparable to the wavelength of those radiation that are being meant. So, for example, if we talk about radio waves, the radio waves are few meters or few centimeters. It can be. So the that's the wavelength is comparable to the sizes of buildings and things like that. If you then bring it down to centimeter side or millimeter, right, then it will become a microwave radiation, and then you're talking about sizes of say flies, right? If you decrease the wavelength even further, and so if the wavelength becomes of the order of a pinpoint, some sort of a comparison, then you'll have an infrared radiation. Again, we can't really see with our eyes. And if you decrease the wavelength further, then we'll see the visible. And the visible wavelength, the wavelength is comparable to the sizes of bacteria, for example. We keep decreasing the wavelength. As I said, our eyes will not be able to detect. It will go into ultraviolet range, and ultraviolet range, that's the sizes of molecules, right? The wavelengths are of the sizes of molecules. If you decrease the wavelength further, then we will get X-rays. The X-ray, the wavelength is of the order of the sizes of atoms, right? How big are atoms? Now you know. I mean, you are you remember your class 11, 12, the sizes of Bohr atom, for example, of the order of an angstrom, right? Half an angstrom is the Bohr radius. So the atoms are of the order of angstrom, and so that's about 10 nanometers here. And oh, sorry, an angstrom is 0.1 nanometer, right, sorry. Then if you decrease the wavelength even further, and wavelengths become the size comparable to the sizes of atomic nuclei, right? That's the gamma rays. So that's a huge range of electromagnetic waves. Now, traditionally, for many centuries, even till a big part of the 20th century, astronomers could access only the visible part. So the universe that we knew was very limited. Now, and how do we get more information when we open the windows of other wavelengths? One example I'll give you. So, for example, this is an example of the same object being seen in two different colors, two different detectors. So, a person is holding here a black plastic bag, okay, and now and this is how it looks like in visible wavelengths, and this is what it looks like in infrared wavelengths. Now, as you can see, here on the left hand side, what we see as the face of the person or the body of the person is through the light reflected from the body of that person. And light is emitted by somewhere else, some bulb somewhere in the room, right? And that light falls on this person's skin, and then depending on the color of that shirt or whatever, right, hair, depending on that we see different colors. On the right hand side, you see the light, this is infrared radiation, and that is light, that is radiation that is emitted by our own body because we are warm. And as you know, we have some temperature, we are warm blooded animal, people, right? So, and there is a temperature associated with this, and so we radiate. Any object which has got some temperature will radiate. And depending on, you remember your black body radiation. So depending on the temperature is going to determine in which range of wavelengths most of the radiation is going to be emitted. So you remember during the COVID time, right? Whenever you had gone to maybe the airport, there was a thermal imaging, right? And that's how people found out, they found out who had fever or not. How was this done? They looked at the infrared image. And in the infrared image, basically the emission, as I said, it depends on the temperature. And if you had higher temperature, higher than average temperature, then your emission signature would be different. And that's how they found out whether some person who is walking down, for example, the airport corridor or something after disembarking from the plane, who had fever and who had not. Right? So this is how, this is a different way of looking at things. You get more information by looking at infrared. Just by looking at a person in visible light, we have no idea whether this person has fever or not. But if we now use our infrared detectors, we get additional information. Likewise, astronomers also have been now looking at objects at wavelengths other than just visible wavelengths. So this is, for example, the sun. This is a very common picture of the sun that you are familiar with. And sun looks yellow, and these are the sunspots. Sunspots are basically locations on the surface of the sun which have slightly lower temperature, and so they emit slightly less, and so they look darker. It's not that that it's dark; it's the temperature is slightly less. Now, why is it less? If I just look at the visible photograph of the sun, it is very difficult to understand the physical properties or the origin of these objects or the phenomena of sunspots, right? For this, we need to look at other wavelengths. If we look at the sun, for example, in ultraviolet image, what happens? You see a totally different picture of the sun. It looks like something in visible light. It looks like a very as if nothing is happening there. Whereas in ultraviolet image, it looks like it's like a violent kind of a place where lots of things are happening. And exactly along where we had seen sunspot in the visible light image, which appeared dark in the visible light image, those spots, those locations now appear to be brighter in ultraviolet image. Something is happening here, which means brighter means they emit light. They emit light more than the surroundings, right? So this is something totally opposite to what we had seen in visible light. You see you get some more information. Now, if you look at the ultraviolet image, this is what if you actually take a zoom in on one of the sides of here, ultraviolet image, you will see something like this. We'll see that these are the visible light sunspots, and bridging them there is some sort of an arc kind of thing, okay, and that is emitting light. It's emitting light in ultraviolet, and that's what causes the ultraviolet image. So somehow the sunspots are connected, it looks like, by some sort of an arch, some sort of a gateway, and that gateway is like emitting light. Now we understand what is happening actually. This is another image of ultraviolet image of the sun. Okay, okay. So that's basically these connect two sunspots. What is this? This is radiation emitted by high energy electrons. And basically what happens, you know what happens to a charged particle when you have magnetic field. Suppose you have magnetic field like this and you have charged particles. What's going to happen? Charged particle basically rotates, gyrates around the magnetic field, right? And if you had some speed in this direction, then it will basically go in a helical manner. And this basically means, what is that? This is circular motion, right? And circular motion means the charge now has acceleration, centripetal acceleration. And whenever electrical charge has acceleration, it radiates. It's a simple physics, okay? So if you have magnetic field, then the electric charges, in this case electrons, basically are going to gyrate around this magnetic field. Okay, like you put beads on a thread, right? Right, and then you can see that they gyrate around that, and as they gyrate around that, they are accelerated by a centripetal acceleration, and then they radiate in ultraviolet, and this is what we see. In other words, this path taken by the electrons basically shows the magnetic lines of force. This is the magnetic line, magnetic field. In other words, there is a magnetic field involved. We had no idea of this magnetic field if we had just only looked at the visible light image. From this, it's very difficult to get anything, any information out of it. Once we get the ultraviolet image, then we get to see all these things. So this is a comparison of what the magnetic fields of light. So it looks like the two sunspots. There are sunspots always come in pairs, just like magnets do. See, the magnets have North Pole and South Pole. They always come in pair. If you break a magnet, you will get two pairs. Right? So it's and the sunspots are always they appear in pairs. And there is a North Pole kind of thing and the South Pole associated with it. And just like it's a schematic diagram shown here. And there's a magnetic field, just like a horseshoe magnet that you are familiar with. And if there are free electrons in the surface of the sun, then they will basically go along in this magnetic field and radiate ultraviolet light, which we can see if we have ultraviolet detectors. Right? Now, there is another part of the sun that we don't see in visible light. So, for the visible light, it's right outside the what is called the photosphere. We don't see anything. It's dark. But if you have seen total solar eclipse, during that time, you will also see for a few seconds or minutes, as long as the total solar eclipse lasts, you should see, we get to see a sort of a glowing radiation beyond the sun. This is here the total solar eclipse image, and the sun, the disk of the sun is blocked by moon, right? And we see a glow around the sun. Where is that coming from? We don't get to see in the visible light, but only during total solar eclipse, right? Now, this is called the corona. This is a part of the sun which is located far beyond the photosphere. And now we don't get to see it because the light from it, the radiation from it is actually very, very faint. And compared to the radiation from the main disk of the sun, which is dazzling, we don't get to see that faint radiation. But when you block the sun, you see it. Now, this sun, this corona is actually very hot. It's about million degrees hot. And million degrees objects, they emit in X-rays. So when you send X-ray instruments into space and take X-ray picture of the sun, this is what you see. We see that the outside of the sun, the gas in the outer region, I mean beyond the main disk of the sun, is glowing in X-rays because it's hot. Okay, and so then, and there again, they're connected, somehow they seem to be connected to the sunspots, and the sunspots are also glowing. Okay, because some sunspots are themselves very low temperature, but what is happening just above the sunspot seems to be very hot. So slowly we can piece together these sort of information and try to get try to understand what is happening in sunspot. What makes a sunspot a sunspot? Why is the corona very hot? I mean, and naturally, what you would expect is that in the core of the sun is very hot. It's like 10 million, 15 million degrees hot. And as we go towards the outer periphery of the sun, the temperature decreases. But somehow, as you go even further, temperature increases. That's very, very counterintuitive. That is not what you expect. So something unusual must be happening on the surface of the sun, which is making the gas above the solar atmosphere, so to say, very hot. So so this is the magnetic field of the sun, and so people basically piece together all this knowledge and to then try to understand. Now, uh, this is an example of how we can use the knowledge of emission different wavelengths and find out more about celestial object. Now, the problems. Why is it that we have only now begun to do ultraviolet astronomy, X-ray astronomy, because of our atmosphere. Our atmosphere allows. So this is the atmosphere of the sun, of the earth, and this is the penetrating sort of length of the depth, of radiation of different wavelengths. Okay, the radio wavelengths can come. Okay, but there's also a range here. Below, say, about 10 megahertz, there is ozone. The ionosphere of the Earth doesn't allow radio waves to come from outside the Earth to come inside, because the ionosphere is basically full of free ions and electrons, and it's like a metal conducting sphere almost for those frequencies. So less than 10 megahertz frequencies, again, you don't get to see any. But more than that, I'm sorry. Yeah, more than that, we get to get the radio. And this is, see, below what I said, below 10 megahertz, light cannot, radio waves cannot penetrate the ozone layer. And that's exactly why radio waves can be reflected off the ionosphere if transmitted from the Earth. It acts like a metal, right? Metal surface. Now, so radio waves can come in. Infrared cannot come in very far because of water vapor in the atmosphere. So yes, either you can send a probe, say, on a plane in the stratosphere, below, above the troposphere. Then it is possible to get some infrared images, or you need put it up infrared detector in very dry places, like in deserts, like in Chile, in Atacama Desert, or high up in the mountains, or you send your detectors up in a satellite. Right? Optical is what wavelength basically reach the Earth, and which is why our eyes are sensitive towards optical. Ultraviolet is again blocked by the ozone layer. So is X-ray and gamma ray. So in order to study ultraviolet or X-ray or gamma ray and infrared here, we need to send space probes up in space, or maybe balloons. But balloons are very they last only for they don't last long. Right? Sometimes you send rockets, and then while they're being launched, you get some information, or you send a space probe, satellite, which are expensive. So which is why these sort of multi-wavelength astronomy has come of late, only recently, in the last, say, 30-40 years, with the advent of our space program, and now India is also a part of that, and I'll show some examples. Now, let me go back to our sun, okay? And this is a full picture of the sun in different wavelengths. So this is the sun as we see in optical telescope. This is the sun as we see in infrared telescopes. and different wavelengths. Okay, and this is the sun as seen in ultraviolet telescope. This is sun as seen in X-ray telescope. Basically, all these information, they always give us some extra information, and putting together, piecing together all this, it's like a jigsaw puzzle. You put together all the pieces and then you get a picture out of it. You get to know exactly what's happening. You know about Aditya L1, the space probe that was sent by India, which has been put in the L1 Lagrangian point, and it is looking at the sun, monitoring the sun. Now, there is another example of Jupiter, for example. How does it look like in different wavelengths? You are probably familiar with this picture in the middle, which is what Jupiter looks like in visible wavelengths. This is what it looks like in ultraviolet. Okay, as you can see, there are some bright kind of arcs in the two poles. These are like almost like auroras in Jupiter. Okay, and in infrared you get to see how warm. So infrared basically tells us the temperature. Okay, because that's the emission that in visible light, Jupiter is not emitting any light on its own. It's a planet, right? So what we see in visible wavelength is the sunlight reflected off the surface of the Jupiter. But in infrared is the light that is being, radiation that is being emitted by, say, the warm clouds at different heights of Jupiter. So, so this is what we get to see. So in a way, you can think of looking at different wavelengths. I mean, looking at an object through different wavelengths. It's like looking, the story of the blind men and six blind men and the elephant, right? Somebody touches the elephant and trunk and thinks that it's like a snake. And somebody touches the tusk and then thinks, oh, it's very pointy, so it's like a spear, right? And somebody looks at, touches the one of the legs, and it's like, oh, it's like it's like a tree, okay? And somebody touches the ear, and then so it's like a fan. The body looks like a brick wall, and somebody touches the tail and thinks that it's like a rope. So it's like different wavelengths, studying different wavelengths, it gives us different pictures. You need to basically piece together all of this information and then build a picture of what an elephant is. Okay, so that's what multi-wavelength astronomy. So I'll just give you some examples which you might find interesting. So this is Andromeda galaxy. This is our nearest neighboring galaxy from Milky Way. And this is what it looks like in visible wavelengths. Now, these are the images in other wavelengths. Now, what does it tell us? So I'd just like to tell you the story of how different wavelengths tell us interesting stories. So for this is optical, right? This is now in infrared and X-ray. So X-ray is shown in blue color. This is blue colors, and infrared in these colors. This is the composite image. Now let's look at on the right hand side. When you see X-ray, X-ray basically comes from what we call the X-ray binary stars. So that's what happens. So in binary stars, there are basically two stars, say, and one of the stars may be a very compact object, maybe a white dwarf, a neutron star, or maybe even black hole, very massive object, and the other star is not so massive. And what happens? Some of the gas from the companion star falls onto this massive companion object, massive object, which is like the white dwarf or the neutron star or the black hole, and it is being attracted by the strong gravitational field of the white dwarf or the neutron star or black hole. And as the gas falls into the gravitational field, it gets heated up and then emits X-rays. And these are the points so where X-ray is being emitted. So looking at the X-ray, now we know where for example, white dwarfs or neutron stars or even black holes are located in, and studying the X-ray spectrum tell us what is happening there. In the infrared light, for example, we see something totally different. Infrared light mostly are emitted by either low mass stars, masses with masses say less than that of the sun, or dust. There's a lot of dust grains in space of various sizes, and these dust grains are heated by basically stellar radiation from the stars. And the dust temperature is of the order of 100 Kelvin or few hundred Kelvin, depending on the distances from the stars. And these dust grains glow in infrared. And this is when you open up your infrared imager, and just like during the COVID time, we had a thermal screening in the airports, and we could find out who had fever or not. Here also we can find out where is dust located, where is warm dust located in Andromeda galaxy, right? And that tells us about a lot of other things, because you need dust to make stars. It may sound very surprising, but we need dust in molecular clouds in order to cool down the gas and where stars can form. So, but that's a long story. It's a different story altogether. But this is an example of how looking at different wavelengths tell us. So this is an example of how it looks like in infrared. Sorry, ultraviolet. Right. So in ultraviolet, emission is being emitted by very massive stars. So, and massive stars don't last for very long. So when you take a picture, hang on for a second. I'm so sorry, but I mean, just hold on for a second. Sorry about that. So I'm in an institute in Kolkata right now. So so can you hear me?
Yes, sir.
Yeah, right. So as I was saying, ultraviolet radiation is emitted by very massive stars, and which don't last for very long. So when you take a picture of a galaxy in ultraviolet, we actually get to see where stars are being formed right now. Right now means in the last, for astronomy, right now basically means last 10 million years or so. That's like right now for us. It's like the present times, okay? Because our time scales are very, very different from the time scales that we are familiar with in our daily lives, right? And so million years is very, very recent for us. So this is Andromeda galaxy in ultraviolet, and the bright spots basically shows the locations where stars have formed in the last, say, 10 million years or so, okay? So here, for example, on the right hand side we see the picture of the dust location. By X-rays we get to see where the massive neutron stars or black holes or the white dwarfs are located, and are basically some activities happening around them. And here you get to see the star formation history. Now again, this is there's a picture of M101. I think it's a spiral galaxy with a lot of spiral arms, and this is again a composite picture. This is as it looks like in visible wavelengths, and this is what we see in other wavelengths. For example, in ultraviolet light shows where recent star formation is happening. Now, India has made a lot of progress, I should say, in studying the ultraviolet universe and the X-ray universe, and both of them are very important. And this instrument was launched in 2015 September, and it's still operational. It has made lots of interesting discoveries. So it is looking at the sky simultaneously in ultraviolet and X-ray. So there's a ultraviolet telescope called UVIT, and the X-ray telescope is called AstroSat. Now, last year, from my institute, Raman Research Institute, a new instrument was designed and fabricated at RRI. I'm very proud to say that my colleagues had actually conceived the design and made this, and I have seen this instrument being built over years and over decades, and it was launched last year, January, and it's called ExpoSat, and And it has the main instrument on board is called Polix, which was designed in RRI, and this is the Polix, and it basically looks at X-ray polarization. And you know that electromagnetic waves are polarized, and just like frequency or color or the brightness, polarization of electromagnetic waves also gives us other information. Okay, and so this instrument is designed to look at polarization of X-rays, and that is supposed to tell us a lot of things about the X-ray binary stars and the X-ray objects, emitting objects. Here I want to show another interesting picture of our own Milky Way. I've shown you Andromeda galaxy, other galaxy. What about our own galaxy, Milky Way? So this is the Milky Way as it appears in the sky of the Earth in visible wavelengths. Okay, you see a lot of. If some of you may have gone to trek in the mountains, and you may have been struck by the amazing sight of many stars in the sky, and you usually can see a band spanning east to west. But amazingly enough, you also see some dark patches, okay, along this band, and these dark patches are caused by dust and clouds which are opaque, clouds which are dense, which are basically opaque, and they basically absorb the light from background stars, and that's why they appear to be dark in some patches. Now, in this Milky Way, if you look at it in different wavelength, this is what it looks like. This is like a Milky Way different wavelengths. Okay, so let me just show you, tell you what each wavelength tell us. So, for example, this is what the Milky Way looks like. The Milky Way is a disk-like object, and we are somewhere. This is the center of the Milky Way, and we are somewhere far from the center. And now, this picture is taken from the vantage point of the Earth. So, and since Earth is solar system is quite far from the center of the Milky Way, it appears like a disk, right? So, so this is what it appears to be in radio continuum, say about 400 megahertz or so, and this radio. And so, for each wavelength, we need to think about the physics of what sort of physical process can give rise to this emission. Okay, so radio continuum is mostly coming from electrons which are gyrating in magnetic waves, magnetic field. So there is magnetic field in the magnetic Milky Way, and there are electrons. And there's sometimes very high energetic electrons which are then relativistic speed, moving in relativistic speed, and they produce this radio continuum. So 408 megahertz, this is like an image. So this is like a image of the Milky Way that would have appeared to us if our eyes could detect 408 megahertz radio waves. Okay, so with radio telescopes, astronomers can actually build an image. Okay. This is what appears is emitted by atomic hydrogen. So atomic hydrogen, in its ground state, it emits a radiation of wavelength called 21 centimeter, and that tells us the location of atomic hydrogen. Where so this is basically tells us where hydrogen is in the atomic form and not ionized. Okay, and here we know where free electrons are there. So it's a complementary information, as you can see. This is radio continuum at a very high frequency, like 2.4 to 2.7 gigahertz. I'm not. So again, this is the same, similar phenomena, but you need very high energetic electrons. So it basically tells us where are the highly energetic electrons are located, and then the question then comes to the theorists: why? Why are they there? What creates this? What makes them so energetic? Right? This is emission from molecular hydrogen. So hydrogen is in the molecular form, which means it's like lower temperature. And these are the cores of molecular clouds, dense clouds. And this is, third from the bottom is what we see in optical. Okay. And as you can see, there are dark patches. If you go to one row above this or the rows above this, you can see the near infrared and mid infrared basically, you'll see that these patches which were dark in optical images have become bright now. Just like dust which obstructs and absorbs and scatters light from the background sources themselves start to glow because they are warm, and that emission can be seen in infrared. Okay, so when we see infrared light and compare with the optical light, and then we can see a complementary information there. In X-ray, this is the last two bottom rows, X-ray and gamma ray. These are the two totally different. So X-ray, I told you, X-ray binaries basically, and there's some, of course, some hot gas, very hot gas, million degrees gas near the center of the Milky Way that emits X-ray. Gamma ray is a different phenomenon. It's emitted by when a very high energetic proton hits another proton in the space between stars, then a pion is created, and the pion then neutral pion then decays into gamma ray. So these are different processes. So again, all these information, all these studies gives us separate information, and you pull together, you gather all this information, and then you start to build a picture, a total picture of what Milky Way is, what all the things are happening in Milky Way, and how are these all connected. So stars are connected to dust. Dust is connected to, so for example, the electrons or the protons or the atomic. Everything is connected to everything, right? So because it's a very complex dynamical system, which is Milky Way, and you cannot isolate. Oh, I'm going to study only dust and not stars. So all these wavelengths, studies in different wavelengths become very important to you, because you cannot isolate one particular segment of Milky Way, right? And so in astronomy these days, this is what I say is a new phase of astronomy in the last few decades. We call it multi-wavelength astronomy, and it has now come to a, it's become almost important that even if you are a radio astronomer, earlier there used to be only radio astronomers, X-ray astronomers. Nowadays you have to be an astronomer in total. You have to know how to think about different processes, different wavelengths, analyze data of different wavelengths, etc., etc. Now, I'll end with a curious thing. Remember, I mentioned that radio wavelengths below about say 10 megahertz cannot come from celestial objects. Okay, which is why radio, for example, shortwave radio, like kilohertz, right? So kilohertz radio is emitted transmitted from radio transmission centers, and they get reflected by the ozone layer. By the same token, any other wave coming from the space will also get reflected off. So how do we get to see the universe in frequencies less than 10 megahertz? There is no other way. So people have been now thinking of, say, going to the moon. The moon doesn't have any atmosphere, moon doesn't have any ionosphere. So radio waves of all wavelengths are accessible from the surface of the moon. So a lot of efforts are now people are thinking about doing astronomy from the moon, and especially radio astronomy. And in that regard, India is also making some plans. So these are like very futuristic plans of making moon station, lunar stations where things may happen. But before that, I think what might happen, it is likely, but I don't know when in the future it is going to happen, is that possibly some radio telescope, people are planning to set up radio telescopes which will gather radio waves coming from deep space, and so this is an example of what I said about Earth's atmosphere. So below about say 20 megahertz or so, the radio waves are reflected, okay? And so this is why radio waves are, that's what makes radio transmission possible, this ionosphere. So ionosphere acts like a block, like a metal thing. And what do astronomers hope to achieve with these studies of emission less than, say, 20 megahertz? Now, I mentioned that atomic hydrogen has a radiation of 21 centimeter. Now, 21 centimeter wavelength corresponds to a frequency of about 1.4 gigahertz, 1420 megahertz, or 1.4 gigahertz, right? Now, it turns out that, if you look at the history of the universe, in the very beginning there was this big bang, and then things were very, very hot. Uh, Gas was ionized, but at some point, when the temperature came down to about few thousand degrees, then atoms formed. Okay, and this is called the dark ages. And then the first stars formed, and the gas again became ionized because of the radiation, ultraviolet radiation from the first stars. Now, in this phase, when the universe was less than, say, about zero point 0.1 billion years, it's about 100 million years or so, right? Around that time, universe was full of atomic hydrogen, because most of the component of the universe is made of hydrogen, and it was in the atomic stage. And the hydrogen atoms basically then emitted in this with radiation. But as the universe expanded, this radiation, which was 21 centimeter, became much larger and larger, because as the universe expands, the radiation coming from so far back in time would have also become stretched by the expansion of the universe. So the wavelength would have increased, which means the frequency would have decreased, and frequency would have decreased from 1.4 gigahertz to below 20 megahertz. So what people are trying to achieve is to detect emission from atomic hydrogen, which existed when the universe was of the order of 100, 200 million years old. Okay, and that is not possible from the Earth, and people are thinking of going to the moon to do that. And that's, taking the multicolored or multi-wavelength astronomy to another level. And I will stop there. Okay, so this is basically futuristic designs that people are thinking of using the lunar craters as a big dish of radio telescopes. Okay, and making some designs there. So I'll end there, and thank you very much for your attention. And I can take some few questions if there are any.
Yeah. Uh, Thank you for your wonderful lecture, sir. So yeah, so we'll move on to the question and answer part. So like we have a few questions prepared from our side. So like the first question, sir. So the universe emits radiation across the entire electromagnetic spectrum, right, sir? Say you
Right?
find a celestial object. How do you astronomers choose which spectrum to focus on, like to get the maximum?
A priori we don't know, right? So you try everything. A priori, I mean, to begin with, we don't know what the object is. So you can never figure out in what sort of wavelength it's going to be the most optimum to study. So you try radio, you try X-ray, try visible, whatever is easiest.
Oh, okay, sir, sure.
And only in the hindsight, only later you would know that this is the most optimum wavelength to study subject.
Okay.
That can come only in hindsight.
Oh. And another thing, sir, like if you observe an object in different wavelengths, you get like different insights, right? Is there like any specific example where you observed an object and with multiple wavelengths and we used all the wavelengths to get a specific insight?
Yeah, for example, the sunspot, for example.
Oh,
So I've been
yes.
giving these examples. For example, sunspots in visible wavelengths, it looks like a dark spot. Okay, it doesn't say much. Once we see the same location in ultraviolet, it tells this says that something unusual is happening. It's definitely not dark, it's actually brighter, so something else is happening. So the same object appears in different wavelengths. So in different wavelengths gives us complementary information. You add this information, you get a total picture, just like the elephant and the six blind men kind of.
Yeah.
Technical
So,
questions.
I have
Like
one question.
Yes.
Sorry, I'll just yeah. So you mentioned about different like examples, like let's say if we observe some objects in space, or let's say we observe some astrophysical phenomena, right? For example, you gave the example of the sunspots, like in the UV, in the visible spectrum, we can see like dark regions and ultraviolet. It's like intense magnetic activity you can see, right?
Yes.
So what I could understand from that is like different, like you are using different wavelengths,
Yeah.
and these like different wavelengths, and it's like basically you're relying on a particular physical process, right, for
Yes.
tracing.
Yes. Yes.
So I
Yes.
mean, does not that create a confusion? Because like this makes the job for the astronomer harder, right? Can we not just rely on one particular wavelength
No, no, no,
and
no, no,
use
no,
it?
no. It's actually it's making it easier, because if you just block our view to all other wavelengths, then it will be limited. You will only get a partial knowledge. And what you're saying, I think what you're trying to say is that when suppose I open up a ultraviolet window and I detect and I image an ultraviolet, how am I going to know what process is important? Is that something that you are asking?
Yes, sir. Like
Yeah, I think that
exactly. Like
yeah,
hmm.
right. So I'll come to that. That's where your physics comes in. We know exactly what. So all astronomers, one of the first things they need to study is the process of radiation. We know what sort of physical process give rise to what sort of radiation. But looking at the radiation and the spectrum, we can figure out what's. It may sound like magic, but it's not. It's just physics. It is the physics of radiation, and it is the physics of radiation is very very important for us. It's right. So um, mm, right now I have just told you, right, that ultraviolet wave is emitted by electron. Now why not proton, you could ask. Why is it not emitted by, say, just a hot gas which is emitting black body? How do you know that? Now that's like all the different these are things one has to study and actually get trained in. So that by looking at it, I know, after many many years of experience, what is likely to be emitted by what.
Okay, so basically you're telling like looking at the radiation, you
Figure
can
out
judge
physical process.
what sort of,
Yes.
but
Yes.
like is there like let's say an astronomer, like a young astronomer who doesn't have much experience, so he
You get
can't
to learn.
do that.
No, you get to learn. I mean, like you keep learning, right? So and in a few years, so with more experience, more and more experience, so that's where the
Right.
experience counts. And
Okay, so but even if we like use, let's say, different types of wavelengths, how do you, but different types of wavelengths, they will give rise to different, like different behavior, right? So how do you
sure.
ensure that that corresponds to the same structure, what you're trying to observe? That's the confusion
Uh,
asking that may create.
I'm looking at the same object. No? I know the say, for
Yeah,
example, the sun.
but we can have like different, like same objects. Let's say we are looking at let's say we are looking at a supernova remnant,
Yeah.
right?
Yeah.
And yeah, but we don't know exactly which one it is. So you're looking
Oh,
currently at
so
one of the,
so if I look at it in optical, then I look at it in ultraviolet, then I look at it in X-ray. I will
but
be
there can be
then.
many supernova remnants like that, right? So how do we know? Because we are particularly interested in studying one of the, let's say, Cassiopeia A,
Sure,
right?
fine. So I'll,
And
I'll take that only. I'll take only Cassiopeia A. I'll only take, and then I'll look at Cassiopeia in different wavelengths.
uh,
And then I'll
no,
find
my
out. See, supernova remnant means what? It's not just one gas made of just one element, right? There's a lot of things happening there. It's a dynamical thing. It has got high energy electrons. It has got high energy protons. It has got just normal gas. It has got some dust particles. A lot of things happening, and each of them are going to give you clues in different wavelengths. If you look at its infrared, you'll get to know about its dust. If you get to see its gamma ray, then you know about its proton content. You will get to see in X-ray, you'll get to see its electron content. And how I know that? How I know from the physics of radiation. And so, piecing together, then I'll get to know, oh, what is the dust? How is the dust related to then electrons and protons, etc., etc. And then I'll do put up a physical picture of what must have happening, what is happening in the supernova remnant, to show in different wavelengths whatever is it's showing. And that is called a theoretical model of the supernova remnant. It's a holistic model, right?
I have a
Right, sir. I
question
got it
about
clear.
the utility of the coronagraph. Can I
Say it
go
again?
ahead? I have a question about the utility of the coronagraph that they use for picturing the sun generally.
Yeah.
So, if we as scientists know which wavelength to probe for, why do we still need the coronagraph? Because given that sun emits more on the UV side, so why don't we build sensors that are sensitive only in the UV side? Why do we still need to use coronagraphs?
See, the coronagraph is still looking at. So, is this coronagraph? Is it looking at UV or?
No, we use coronagraphs to hide the
Right.
photosphere, right? Why do we still have to use it? Because we have realized that the UV is the most.
Yeah. Well, it's not very easy to build a UV telescope, See, UV telescope, as you go to shorter and shorter wavelength, the mirror accuracy has to be very, very high. The surface accuracy of a mirror, it is comparable to the wavelength. So if you go to shorter and shorter wavelengths, the mirror has to be extremely highly accurate. That's very difficult.
But essentially, we still have to look at the UV. So at the end of it, we should have the UV telescope.
Sure. But it's easier to do a coronagraph and then to make a UV telescope. So both of them, there are pros and cons of, and we do whatever we get to do. You don't leave any stone unturned in a way, right? I mean, you use all the avenues that you can use.
Right.
Okay.
I mean, astronomy is a very handicapped science, We are all bound to this earth and we are trying to think of the whole universe. It's a very handicapped science. We can't bring sun to our microscope or in our laboratory and find out what's happening. So we use whatever is available.
Right.
Okay.
Professor, am I audible?
Yes.
Yeah. I have a doubt about how you observe black holes, because black holes emit in a lot of spectrum, right? It has a wide spectrum of emission.
So black holes don't emit anything. I mean, it's like I'm not talking about Hawking radiation here, but the gas which is falling on black holes emit radiation, and that's we can see that. And sometimes it's mostly it's X-rays.
So yes, sir. How do you differentiate a black hole from anything else? Like how do you observe?
So we need to look at the X-ray spectrum, and the X-ray spectrum will tell you basically. This is it's a difficult thing. How do you know that it's not a neutron star or a black hole? That's a very technical kind of a question. I can't tell you in a few minutes. But basically, studying the X-ray spectrum tells you that. In a way, so X-ray spectrum tells you what? I mean, if the stronger the gravitational field, it will basically pull the gas with more speed, and so the gas is going to get heated to higher temperature. In a simple way, the temperature will tell you something about the strength of the gravitational field, or whether it's a white dwarf or a neutron star or a black hole, right? So that's like a very simplified picture, but there are more technical things into it.
Thank you, Professor.
Sir, I have a question based on that. Sir, the first picture of a black hole, at least the accretion disk of a black hole, was taken just a few years ago. Why did it take so much effort to take that one picture? Couldn't we just point a telescope near the black hole and take a picture of it?
No. Wow, that required coordination of so many radio telescopes. So all the radio telescopes on the Earth had to be coordinated in such a way that the whole surface of the Earth was like a one big radio telescope. You see, you remember, it's basically something to do with the diffraction. And the diffraction, the larger the aperture size, okay, the diffraction pattern depends on uh, the aperture size and the wavelength, okay. And you're basically doing a two-slit interferometer here. So all the radio telescopes are being used as an interferometer. Okay, so it's very, very difficult to use, for example, radio telescopes across the continents. How do you know the timestamp? How accurately are your time being recorded? Okay, and they have to be recorded depending on the wavelength and the light crossing time. So it's actually very, very difficult technically. So you can't just point a telescope and then get an image.
That makes sense, sir. And sir, as we are running out of time a bit, I
Yeah.
guess you have some work. There are some questions that have been asked in the chat. I will tell them out for you. So the outer layer of the sun is much more hotter than the inner layer, and
Yeah.
apparently we still don't know the reason why. Like, is
Yes.
there any reason, sir?
Yeah. Well, I mean, it's something to do with the sunspot activity. I mean, there's something to do with the magnetic field, it looks like. If the magnetic field does something to whip it up, the gas, basically, somehow the magnetic field energy is being transferred to the thermal energy of the gas. That's how. But how the transfer is happening, the detailed physical process is still people are studying.
That makes sense. And I believe Arundhati has a few more questions to ask. I think Arundhati's mic is muted, so I will continue with the questions. Just a few questions, sir. Like the
Yeah,
discovery of the
yeah.
yeah, okay.
Okay, I'll do it. And yeah, so like, what inspired you to pursue astrophysics? And like, after
Me?
these many years, like,
Yeah.
what inspired you to pursue astrophysics? Like, even after these many years, like, why are you still interested in it? Like,
Why am I still interested?
what keeps you motivated?
Well, first of all, I don't know. I'm not skilled to do anything else. So I like what I do, and why I became an astronomer because well, I had a telescope when I was in class 10. My my parents gave me a small telescope, and I grew up in Assam. It's a small town, so the night sky was very beautiful. I could see the stars, and the telescope. I started using it to study the moon, for example, and I used to look at the craters of the moon, and I became so fascinated that I just never looked back. That's it. I mean, my life was doomed. So, and well, I'm still interested because I think every day I find new things to learn. There's so much to learn. And yeah, keeps me going.
Yes, sir. Okay, like you have written extensively for these newspapers and public. How important do you think science communication in today's world? Like, and what advice would you give to the young students who are interested in science and like writing?
Well,
Any tips
you
for
see,
them?
I think science communication is important because, first of all, um, we need to have a society that thinks scientifically. And it's not just the students. Although I'm talking to you as students, my target is to talk to general public and to make them think in uh, in a scientific manner about everything. And if we can't have that, I don't think we will have a sustainable society. I mean, if we really think about what we should do to our environment, what we should do, around us, we need to think scientifically. And for that, science communication is important. It's not just about, oh, some new discovery has been made, I have to tell that to the new general public. It's about making scientific temperament, a society thinks scientifically. That's what I think is important. Which is why I actually write in Bengali also, because that's my mother tongue. Because I think a lot of people in India, they don't know English, and I have to reach out to them. And the regional languages are important, I think. You're muted again.
Thank you.
Thank you so much. Yeah.
Yeah. Thank you so much, sir, for this
Thank you for having
fascinating
me.
talk.
Yeah.
It was truly enlightening to listen to your insights, and your work continue to inspire young astronomers and space enthusiasts like us.
And to
Thank
That
you.
all our
talk was
attendees,
really good.
All the best. Yeah. Thank you.
thank you, sir.
Thank you, sir. Have a wonderful evening, everyone.
Good night. You too. Bye.
And to all our attendees, we appreciate your participation and enthusiasm in today's session. Once again, on behalf of Nakshatra and NIT Trichy, we extend our heartfelt gratitude to Dr. Biman and for sharing his knowledge and experiences with us. And once again, thank you and have a wonderful evening.